I just want to now tie path models into our ergodic versus non-ergodic spectrum. So obviously we have our global ground motion models. They're pretty much fully ergodic. Then we can have our broad regional models, which are a little bit better. We distinguish differences in China versus California versus Japan, but they're still pretty ergodic. Then we have local models. Now we can distinguish Northern California from Southern California a little bit better. To our left, closer to the fully non-ergodic, we have our cell-based methods. And this is where the level of your cells can get into it. If you have a coarse cell, essentially it's still pretty much a local model. If you have a really fine cell, now you're getting more non-ergodic, but it's still, there's some physical limitations of the model. From this, we can see that there's kind of a range of typical path models that are being developed today. You have your regional methods, which are a little bit better than ergodic models, but still average over a pretty wide area. And then you have your cell-specific methods, which do a better job, but they're sometimes hard to implement because there's a lot more sub-calculations that you have to run, and it's just a little bit more complicated of a model, and there's some physical limitations. In this presentation, I'm going to present a sub-regional method. So this takes the advantages of what we use in regional methods and incorporates the math that cell-specific methods use. So obviously in the next section I'll show, or in 2 sections, I'll show really what this is. But with path models, it's my opinion that we could never go fully non-ergodic because a path is a distributed thing. A path is between point A and point B. You can't necessarily just have one point to represent a path, which is what the data are. They're just points in intensity versus distance space, for example. So the real question is, can we get to what we would consider a practically non-ergodic path model? That's the holy grail of path modeling. And by this, I mean, what level of complexity that also incorporates physical constraints in your model development can you achieve as accurate predictions as possible given your data set, where if you were to increase the complexity of the model, you don't see any improvement of your predictions. So we want the simplest model that gives us the best results. That's practically non-ergodic for our purposes. And that's kind of a major point of today's talk.
I have a question on that. Yeah, I like I like this analogy here. But so your sub-regional models, okay? Of course they have such a wide spread, and you've put in this study there. But where do you see your study actually being in this wide range that I assume is also logarithmic? Is it close enough to where would you place your study, in your opinion, with respect to these other points?
So that I have a slide at the very end, which kind of talks a little bit about that. Spoiling it a little bit, I would probably place the model that I'm presenting somewhere in the middle of a coarse-based and a fine cell-based method, just because our purposes weren't trying to achieve non-ergodic path modeling. It was we had other methods, other reasons why we did this work, but we think that a subregional method could eventually get us to getting the same level of performance as a fine method, but simpler, i.e. less regions you can use. That's the advantage of a subregional method, is hopefully you can use less subregions to get the same results as the Kuhn et al. Model, which had like 500 something cells, which is quite a lot.
So let me understand what you're saying. So I almost would redraw this in putting, this is the fully non-ergodic, and I would put in the Holy Grail on a different path here, right? Mm-hmm. And so this is the practically non-ergodic, and therefore at some point here, this curve would diverge into something that looks like this. And so on this path, maybe your method is here, your recommendation would land here, while the cell base is closer. But in the practicality, this fine base would actually be a lot less practical because we don't have enough data. So here, I'm going to change pens. So you're here on this scale, but you would be here on that curve versus a cell-based, which is great in the Bay Area where we have a lot of data and all that. So that would be here in this case, but it would actually be here in the practice because it's not so practical. And so if you're weighing practicality, which is important with where we are, then maybe what you're presenting is a little bit more general and therefore can be expanded to, you don't need as much data, but you do need an understanding of whatever it is that there are components, right?
Yeah.
And so maybe that's how I would see it, is like, hey, yes, this would be ideal, but we've got to take a different path and think about the practicality of it.
Yeah, I think that would be a great way to better present how this is. I'm a bit disappointed that I didn't think to do that beforehand.
Oh, that's okay. That's why we're doing this, to learn from each other. So,
yeah.
So it's big. I'm big on, I don't read words so much. And so for me, graphics are really important. And you've seen that I question each one because your brain processes it faster than your consciousness does. And so if you put a picture like this, okay, I understand. You almost didn't have to say any words and I could just go on to the next slide, which is how I do most of my paying attention to presentations. But maybe something like this is like, okay, but and this applies to so much in modeling that we're doing as well, that we just don't have enough. And so sometimes we have to go, because you have to think about also, and this is what I learned from the conversations with Norm, is that you can have a really nice model with, and it's funny in the conversations, but I also see it a lot with OpenSeas, is there's these really nice models, but they've got 100 input parameters, right? That one is we don't know what they are. Two is there's the variability in them. And so when you put these models into a hazard analysis, so if you have to do just one little deterministic computation, it's one thing. But if you put this into a machine, now you're real, and having to do a hazard analysis, one additional iteration on, the location of your hypocenter, or one additional iteration on something, well, it becomes additional iterations on 100 parameters, it just becomes impossible to do. And so when we're looking at hazard analysis, we have to think about practicality and computational efficiency almost. But I think here you're more talking about not having data, but I think we also have to think about the simpler, the better, the smarter, the better is really, it's not about simplicity, it's about smarter and weighing all these different things.
Exactly.
So, cool. Thank you.
Of course. Thank you. I'll wait for you to clean that up.
Yeah, let me clean up my mess. There it is.
Great. So now I just want to briefly go over some of the ground motion data that we have available to us. So as you're aware, Sylvia, we've had quite a bit of collection efforts in recent years that have been performed in a consistent manner as NGA West 2, where we've added quite a lot of data. So in this map on the left, I'm showing the locations of NGA West 2 earthquakes, which are shown in the blue. Then all the new data are the other color events, the red, the yellow, and green. And you can see we've added a lot of data, especially in Northern California. And in a similar manner, just as we've added new events, the state has also been instrumented up and down quite densely in some areas in recent years. And so you can see all these new yellow triangles, which weren't there before. So this means that we can have all these new recordings for these new events. And if we look at just
wait a minute. You can't just put dots on a map and good try. All right, I've got you here. So, okay, this is fascinating. All right, so let's look at these two figures. So the one on the left, you've added a lot of data, but it's not like you can add data. I mean, the earthquakes, we just haven't had any really good earthquakes yet. But there isn't, so what's this? The only one that really stands out is this green one here that seems bigger. Is this Ridgecrest or?
Yes. Yeah, so that's the Ridgecrest sequence.
Okay, so there's two bigger circles there. Because everything else seems more moderate size. But yes, we need a big
So you
earthquake.
shouldn't think that size matters.
Oh,
In
because
this case, we care about paths. Size matters, especially if you're trying to do an empirical nonlinear analysis, because you need large shaking. But in this case, even the small strings can be useful, because path effects, we assume, in most cases, are going to be a linear kind of phenomena. We don't assume nonlinearity in the path effects. So the small magnitudes are just as useful as the large magnitudes. It's just with large magnitudes, we get much further distances that we can use.
right, and especially since these smaller magnitudes are in the densely populated areas. So there's actually a lot more value. And even if we then look at not just population, but instrument population. So you're saying there's a lot of value to these little red circles because that's where we have the instruments. And that's where we're really interested in the data, because even a small magnitude, in this Bay Area, that Ridgecrest looks big, but they don't care. They didn't feel it. That's where I was at the time. And so these smaller circles are actually more important than the big circles, because I'm interested in the local hazard and the earthquakes that are going to happen right underneath my house. Okay, and so that's important. So as much as we think, oh yeah, big earthquakes, but for understanding the models, these smaller magnitudes really matter. And that was actually a strength of the NGA West too. So,
Yeah.
Okay, so now let's flip over here to the right. This is so cool. What's this line here of instruments? Is that the Parkfield array or something like that?
Yes, so that was a temporary deployment of seismometers where their primary concern was trying to image the Central Valley Basin, just get a cross section of the basin right here using passive waveforms. But because they were seismometers and they were put there over a span of 2 or 3 years, I think, they also recorded a number of earthquakes. So even though they were installed in this location for different purposes, we get in the modeling world of ground motions, we also can use their data that they collected.
That's that time component. So, okay. And then what's going up? What is this? Utah? Nevada? What's all
Nevada.
these dots in Nevada? Is that storage site?
These
Yucca
here,
Valley? Yeah, Yucca Mountain.
this was another study where they were trying to image some valley. I'm not exactly 100% sure on the details, but it was also a temporary deployment of a line, essentially, of stations.
Okay, fascinating. It'd be neat on this map is to show the USURF faults or
Yes.
some sort of faults. USURF faults are just the easiest because the other ones just get really busy. But I think it'd be interesting to show that, yes, we have most of the instrument on on these faults and things, and especially the earthquakes. I guess the earthquakes tell you where the faults are.
Yeah.
So, fascinating. Okay.
Great.
Thank you.
So from the combination of these earthquakes and these seismic stations, we have observations. And so this kind of just summarizes the comparison of what was available for NJ West 2 and what our larger data set has. So here I'm plotting magnitude versus distance. The red is the new data, the blue is NJ West 2. You can see most of our observations come from relatively small magnitudes between 4 and 5, which again might not be useful for hazard scenarios, but they help us understand the phenomena that are going into the ground motion models that hazard calculations use. And also at far distances, which that's especially useful for a path study, because the more observations you have at far distances, hopefully you can resolve path effects greater. And this plot over here just shows the number of usable records per period that we can use, because obviously we can't use data depending on the corner frequencies that are used during signal processing. But you can see that our total data set is about 26 or 27,000 records, which includes NGA West 2 and the new records. And we've pretty much doubled what the NGA West 2 data set was just with really far records, so records that are greater than 100 kilometers from the earthquake by themselves. So you can see that this data set is a lot richer than the original NGA West 2 data set. And to highlight that with this study, I just want to show the paths for a moment. So these are paths that NJOS2 included. Obviously, the earthquake shown in blue, the small black dots are our stations, and the line are the paths. You can see, again, similar to what I showed previously, good coverage in Southern California and around the Bay, but not a lot of good coverage in other parts of the state. Whereas with this new data set, the red earthquakes are the new events. You can see we've pretty much filled in all of Central California. We've pushed really far north, and we've also pushed quite a ways to the east, especially around Reno and Tahoe area, where there are quite a bit of earthquakes that occur. So you can see with this distribution of paths that we have, we can hopefully better characterize path effects in a much greater part of the state. It's really just kind of this northeastern part of the state and maybe some of the southeastern part of the state where we don't have significant numbers of data. So any comments on these?
Yeah, I didn't unmute myself. Okay, so this is cool, but I mean, these could all be connecting tiny little segments anyways, and so we're not really spanning across. So it'd be really interesting to plot, especially the ones on the right, the ones on the left are, and I don't know if it's possible, but all your line, add another dimension to your plot. So all your lines are yellow, and so maybe color coding them on distance would be one thing, which, the yellow, the short distances to show, hey, we do have a lot of, long distance ones as well, and it might highlight the ones that stand out. Then maybe layer them by distance so that you see those best. Or the other way I was thinking is, that span, highlight the ones that actually span all the way across, because maybe you may not be actually spanning all the way across. And maybe these are small that you're measuring really far away. And that's kind of, if you go back to your previous plot, yes, you have a lot of records. Yeah, so this is the one. I mean, it's not our choices to kind of data that we have, but, oh, wait, I draw. It'd be nice to have more records in this range. And so, yes, you have a lot of records, but, oh, in this block versus, you've got small magnitude, large distance, which is, of course, it has value, but I think it'd be interesting to show we haven't really added much data here. But as you said, again, and that's why we need to put this on the map, because in the map, it actually shows you that this is of value because this is where we are highly populated. And so I really like how you did the second visualization. It's like, oh yeah, they're small magnitude and distance, but they're pretty much local effects. And therefore, that's a pretty high amplitude of spectral accelerations because you're close. So that's all I got.
Yeah, thank you. Yeah, I think that those are good suggestions to improve these figures.
Yeah, but I like the point that you're making. A small magnitude underneath your feet is way more important than large magnitude far away. And a lot of people don't, it's hard to process that, So, and then there's the whole probability of which one is going to go first is also different. And so I think it's important to get that across to people. So cool, thank you.
Great. So next, we're finally getting into some of the nuts and bolts of the model, and I want to get into how we chose to subregionalize California. So there's different ways that anyone can choose to do this. I'm going to present kind of the three factors that we considered when we defined our subregion. The first is we started off with some physiographic provinces that other studies have used. These are generic blocks that have generally consistent properties within each block. For example, we have the Sierra Nevada, which is a big batholith structure in this range. So that's just one region. We have the Central Valley, a big basin structure, and so on and so forth. So we wanted to start off with these starting blocks, essentially. The next thing is we look.
Wait, I got a question on that. Well, no, because so earlier you showed the plot, the very, very first figure. You don't have to go back to it, where you've got the earthquake happening really deep, but I guess our earthquakes are not that deep. And so my question is, and you've got the wave traveling underneath and then coming up the basin, right? And so are these blocks going all the way to the center of the earth, or are these superficial? And so are these in our path, since we're looking at a 3D or 2D effect in the first place? So are these blocks just literally physically deep enough to make a difference, or is that something you take into account?
So these blocks, from my understanding, the way they were derived, they take into consideration topographic features, and then also kind of general environmental conditions. So it's not necessarily that it goes all the way to the core of the Earth, but it probably extends deep enough to where the depths impact our paths, because our earthquakes don't happen more than 30 or so kilometers, might be the deepest shallow crustal earthquakes that we really see.
Okay, so that's important to our regionalization. And just to make sure I was making fun of going to the center of the earth, but at least the mantle, or what is that? The crust.
Yeah.
But the crust is deeper than
the
these.
crust is deeper than these, most likely.
But these affect our path, especially since we are looking at, in California, we have shallow crustal events. If we had something way deeper, then things would be different in the first place. So
yeah, for subduction earthquakes, I think you need a different mechanism to look at.
Yeah, becomes three-dimensional if they're that deep. So okay.
But that ties great into the second thing that we looked at, because we understood that those were very superficial layers. We looked at depth dependence on rock quality factors. So this is essentially a property of the crust. You can think of it as inversely proportional to the anelastic attenuation coefficients that we've talked about. So high values mean that the rock is very strong, so it's going to have less damping. Low values mean the rock is pretty weak, so it's going to have high damping. And so in this case, you can see there's obviously some depth dependence. But what we wanted to look at in these plots was, are the general regions that were drawn in the physiographical provinces consistent with the spatial trends that we see? And again, tying back to, for example, the Sierra Nevadas, you can see that subregion is mostly green and blues at a lot of the depths. If we go down to 20 or so kilometers, even so, when you go deeper, it's generally consistent with itself. The exact values may change, but within the subregion of it's pretty consistent.
And so they don't dissipate. They're pretty elastic, as you're saying, right? They're rock, therefore blue means they're not attenuating much. It's just like a metal running right through rock kind of thing. Okay,
Precisely.
so that helps me to understand the other colors. So the blue is the most elastic material.
Yes.
Okay, and they go all the way deep because the Z is the depth that you're doing your cross section at.
Yes.
Okay.
But there were some regions where we see issues, and an example would be the coastal provinces, which span pretty much all of the northern coast down to San Luis Obispo or so. And kind of the depths to mainly look at is, if we look at depth around 8 kilometers, we can see the northern part of the coast is more red. And then as we move to the central part, a little bit south of the Bay Area, it's kind of yellow, a little bit green. And then when we get down to the very far end of the coastal range, it's coming back to be a little bit orange. So even within this subregion, there's differences. So the province of the coastal ranges is what this province is. There's some province variation. So maybe these provinces need to be broken down. Maybe they can be combined. In some cases, we can see that some of them are kind of consistent, like the peninsular and transverse ranges down in Southern California are pretty similar for the most part. So maybe we can combine some of these smaller regions. And so then the third thing we looked at, because we are empiricalists, is we look at the data itself. So we looked at, on event-by-event basis, for events that reported lots of observation, what do the data suggest? So this is just for a single earthquake, and you can see that we see this bend down at far distances, suggesting faster attenuation or higher rates of attenuation.
Wait a minute. You're plotting a residual. You're not plotting.
Yes. So this is a
intensity measure.
residual with a residual versus distance.
Okay,
So-
and your 0 is right there.
Yeah.
Okay, it's always good to look at where the 0 is, right? That's what I was
Yes.
taught. You see residual, you got to find your 0. Okay, so it's interesting because part of it is above, because the red is, I guess, is the average. Part of it is above, like you were saying, and then part of it goes way below with distance.
Yes.
So,
And the big
okay.
part for path effects, we pay attention to the far away distances. There can be other reasons why the near source observations are funky, but for path effects, we look at the kind of anything greater than 100, really. And so if we do this for many earthquakes, where if I color the earthquake pink for if it's really negative, so going down, the cyan for if it's starting to bend opposite direction, if it goes upward, you see some clustering of the colors. For example, in the north, we see a lot of pinks. There's this one cyan that kind of sticks out a little bit. Over in Reno, they're a little more neutral, with maybe slightly averaging a little bit towards the cyan. We see some transition in the coastal range. And so this suggests that maybe the coast range has some transition, so we need to subdivide it a little further. But some of the clustering in the other subregions aligns, or some of the other clusters that we see align well with the boundaries that were given in the physiographic provinces. And we do this for many intensity measures, not just one.
Right, because so if you go to the previous plot, you were plotting it, oh, distance, not period. Okay.
Yes.
All right, and you do this for different periods. Okay, I was seeing that as period. I'm used to, okay, now this makes sense better. Okay, and so this is just 0.1 seconds, and you could do this at different periods. Okay.
Yeah. And so by looking at these observations and everything that we looked at, we also consider geologic maps and fault maps because we know generally some faults coincide with big differences in rock properties. We came up with 10 regions. So we have Basin and Range, which is very large. It's pretty much all of Nevada and it spills over a little bit into California. Sierra Nevada, Central Valley, South Coast. The only thing I want to mention before I go to the next slide, which this figure will still be there in a slightly older format, is that we broke up the coast range so that we have the North Coast, the Bay Area, and the Central Coast, because we saw in the evidence for the rock quality factor and also the event-specific attenuation data that would suggest that the attenuation in these areas is a little bit different.
Okay, I have a question.
Okay.
The basin range that you've got, there's like this little triple junction right here in the below the Sierra Nevada and the East California's shear zone.
Mhm.
What's going on here? I mean, it's interesting that there's a line here. Was this some sort of, because I remember Sean told me that the Sierra Nevada, California used to be a subduction. And so I'd love to learn more about all this in a different presentation, but here you've got it. It looks really evident in this dot here. So what's going on here?
So I believe that this line coincides over a good distance with the Garlock fault down here.
Yeah.
So my understanding is that there's a pretty big distinction between the two rocks on either side of the fault. As far as why everything joins here, I'm not too familiar with the geologic history of Southern California. I'm more better with it in Northern California. But it is interesting that they all kind of converge to this single point down here.
We'll do our homework and find
Yeah,
out.
yeah, that's a follow-up study.
Yeah. Cool. Thank you.
Of course. So with these subregions, we have 10 subregions. I'm not going to go through the names because not necessarily too important. We're more worried about what's actually shown. I wanted to show the paths again that we had, and you can see that with these subregions, pretty much all of our paths, except for the northeastern California, which is up here, and parts of the Basin and Range subprovince, have pretty good coverage. So we suspect that with these subregions, they're pretty large, which we admit, but we think we can get the average attenuation for these much smaller areas than California as a whole. And so that's essentially the question that we're trying to ask is, with using this kind of coarse subregion, can we get the major trends that we see spatially with path effects for California?
So this is interesting because in you're going back to our original discussion was, you improving the fine, you've got these fine meshes, and that becomes computationally intensive and data intensive. While here, you're just blocking them by something, and let's test if this theory works, that it's really about the physical phenomena that are in the regions. It's a little tricky because, and it's fascinating, maybe it's related, is that the Bay Area and the Southern California, you also have the most data there as well as the most sources too. So it's interesting, like you're saying, it's difficult to separate the path from the source. So okay, cool. But I like this idea.
Thank you. Yeah.